Okay, good morning, everyone. Respected sir. So, uh, we will be discussing analysis of elastic strains. So, as you have all gone through the theory and the basic assumptions that how to consider deformations in a crystals. So, what we do, we consider the elastic properties of crystals viewed as a homogeneous medium rather than a periodic array of atoms. We make use of basic physical principles, that is Hooke's law and Newton's second law. And the small strains are directly proportional to the stress in this case. And again, strain components are specified as EXX, EYY, EZZ, and so on. And other thermodynamic changes, that is adiabatic change or uh, the thermal changes which can be deformed the crystal, we just ignore them for this case. Let's start with the three orthogonal vectors that we have in a uh, as a reference point in a crystal. We imagine three orthogonal vectors as you see here, x, y, and z. I've wrote them in a bold letters, and they are unit length. Means they are in a bold means they are vectors, and they are in a unit length of a unit length. And after the deformation, these are distorted into the new axis. So the new axis, that is x dash, y dash, and z dash, they are written in the form of a old axis, like this here shown, that x dash will be equal to 1 plus exx. For now, we just stick to the three axes that they are transformed, extended, stretched in a way that along x-axis there is a, for this case, before deformation we
Hello,
considered.
hello,
Yes.
Rahul.
Hello.
Please use the
Hello.
cursor to point out the. Please
Okay,
use the
okay,
cursor.
okay, okay. Okay, okay, thank you, Sandeep. So for now, before deformations, we considered these axes. Along these axes, they are of a unit length, but after the deformation they will be stretched. That's why they will be there will be a little deformation, a change to their length. So we wrote them as, if they are of a unit length, they will be get extended like exx, a small change. That's why we have written like this. And if you open this equation, uh, what you will get, that x and exx with the extension along x-axis, and y dash, for y dash, if you open this, you will get another equation like this, and extension along y-axis. So what are these coefficients? These are dimensionless quantities, and equation 2 here, this equation here shows that the new axis will not be of a unit length, that they are be extended. Okay, so now let us consider the effect of deformation. We take uh, okay, right here, uh, uh, we take a point P, say here, the position vector of R, and after the deformation, after the transformations, this will be transformed into R dash. So this, I can write this as capital R. This will it will tell me the displacement along, uh, displacement in this space. Okay, so so what you do, you have R, the old position vector, and the change in the position vector R dash. You simply and this R will tell you the displacement. So you plug in the values, and you will end up with something like this. And I think you all have got right here, everything fine. Okay, so and then you replace this quantity here with u and v and w, and these are unit vectors. So this r can be written like this. Okay, so and what are u, v and w? These are the projection displacements. That u is the displacement along x-axis and v is the displacement along y-axis and vice versa. So one way to do the, rather than the Taylor expansion, we can, what we can do, this is actually from another book. So what we have done right here, the extensional strains, we define, uh, for our understanding, we just take a two-dimensional axis. Okay, so a to b and a to c, we take a frame, and with respect to the reference frame 0. So this will tell you that from before deformation, this frame ac to ab, this will be at r vector, position r vector, and after the deformations, when there will be change, this will be transformed into r dash. So
I request all the students, if they have any question at any stage, please ask so that Rahul can accordingly explain it.
uh, yes, so any questions so far? Okay, so what I do here, I take ab is equal to dx, this length ab is equal to dx, and ac, this length, is dy. So the position vector a is r, that I have defined. So after the deformation, a dash b dash and a dash c dash will be the new axis with respect to origin o, and with position vector r dash. So the if the displacement of a on x-axis is u, see, from here to here, from here to here, I write it u, that is displacement along x-axis and of this point A. So what will be the displacement of this point B along u-axis? It surely will be u plus, okay, u plus, this is a change in the dimension that of u along x-axis and dx. So this will be, I call it, okay, actually they call it a extension, increment in the x-axis. Similarly, we can go on the y-axis, that is a c. So a dash c dash, and if this small displacement along y-axis is v, and then the displacement of b point will be like here to here, this will be v plus the change. Okay, so according to this, so u of r, this will be x-axis, along x-axis displacement of u, and along v-axis. And if you take the three-dimensional case, you will just add the w, the displacement along z-axis. So similarly, what we can do, okay, I've done this, actually I've explained this here, that this will be the increment, this will be the increment along x-axis, where u is the displacement. Okay, so increment along, what will be the increment along y-axis? That will be this plus curly v upon curly x dot dx. Okay, so elongation, what is elongation? Elongation is actually, okay, let me bring up the graph again here. What is the elongation? Elongation will be that is your original displacement to the this change in the displacement to its original displacement. That I've ये यहाँ पे लिखा हुआ है ऐसे, ठीक है. So u plus elongation, this will be total change. So you minus this will cancel out and you will end up with this. So this is the elongation of AB along O axis. This is O, this is X. This is the elongation of how much is AB is transformed along X axis. So this will be the elongation. So unit of elongation, now what you do, this will be the you just write here EXX, that will be the unit of elongation. So what you do, the elongation of AB divided by to the original length. Original length we have written original length is of AB is dx. Okay, so change in length to its original length, it will give you the unit elongation, that is curly u over curly x. Similarly, you can do on the y-axis the change in elongation, you write it as EYY, and change in elongation, that is v minus, like this, v minus curly v upon curly x, y dy minus v. So you will end up something like this, and divided by to its original length, that is d of y, that we have taken AC. AB we have taken DC, and AC we have taken dy. So this will be the change, curly v over curly y. Similarly, you can find out for EZZ axis, it will come out like this. Okay, so any questions so far? I mean, आपको ये समझ आ गया यहाँ तक कैसे ये चेंज हो रहा है?
Yes, sir.
Okay, so
PG
Rahul,
students, any response from PG students?
हाँ जी संदीप,
we can
एक्चुअली
find
मैं
these
Himanshu, Komal,
elongation.
Chetna, Ankit. Yeah, are
हाँ
you
जी हाँ जी,
getting it? Other students I am
Also
asking.
derivation direct from the graph. If we consider u and u plus delta u or del x into dx, that is the del u or del x gives us unit change in u direction per unit length. Okay, so
yes yes
that means we get here from elongation of AB, del u upon
yes
del x also gives the change in u with respect to x, that is unit change in
yes
u per unit length divided by total length, that is dx.
yes
This gives the direct
yes
strain in x
yes
direction.
yes yes yes.
So without doing that, we can directly calculate from here.
No, yes you can do that, but see what you have to do. कि आपको क्या करना है, आप हम क्या ले रहे हैं यहाँ पे, एक रेफरेंस पॉइंट ले रहे हैं, हम देख रहे हैं कि अकॉर्डिंग टू रेफरेंस पॉइंट हाउ द चेंज इज हैपनिंग. Without reference point, how you can say that AB has transformed into some other, AB has transformed into some other place and some other space, and there is an extension. See, there is AB with R vector along this reference point. So this is AB, only dx. That if an observer is here, if you are here, okay, so you are saying, okay, with some instrument you are saying this length AB is dx. If if there is no reference point, if you are not here, if no one is observing it, how can anyone say that AB is dx? That's why take a reference point. So I think that's the way to do it.
Okay.
Rahul,
You got, yes sir.
even if we would have taken Taylor series expansion of your function, then I think things
Yes
would
sir.
have been done very simply. Diagram is good to illustrate things.
Yes, sir.
But what could have been done is that maybe if you have a three-dimensional function which has three independent coordinates x, y, z,
Yes, sir.
then if we try to write down its change, uh,
Yes, sir.
then we need to write down the Taylor series with partial derivatives, isn't it? Like
Yes, sir.
suppose u, v, w are the components of the displacement along x, y, z direction.
Yes, sir.
Then the
Yes, sir.
total change in R should be
Mm,
actually x into del u over del x along x cap. Similarly, y into del u over del y along x cap along. I mean x cap जो x cap के along change हो सकता है. That
yes,
can
sir.
be because of change in u because of x, or change in u because of y, change in u because of z. Similarly, there can be three components of y displacement. That is a change in v because of x, change in v because of y, change in v because of z. Because u, v,
Yes, sir.
z are in general functions of x, y, and z.
Yes,
Right.
sir. Yes,
So
sir. Yes, sir.
maybe that could have been done, but that this is also fine. Okay. Which book you have followed? This book is by what? Which author?
Sir, it's from Gupta Kumar. It's an Indian
Okay.
author. Yes, sir.
Okay.
Sir,
But there is
actually,
a
yes, sir.
yeah, please.
I
Rahul.
was having problem interpreting the Taylor series.
Hmm.
I've somehow done it. I've tried it actually, but there will be actually the equation contains the coefficients inside the coefficients.
Yes, sir.
Like this,
There is problem in
as you heard.
expansion.
There is a problem with expansion.
Yes, sir. Expansion of Taylor series. There is a
So
problem.
that's why.
No, I don't think I have done it just today. There was no problem to me. That's why I expected you to come with the Taylor series. Then we could have discussed it. Maybe.
Yes, sir.
What was the problem? I don't know. Sandeep?
Sir, actually, when we differentiate,
Okay, let me click the photograph of what I have done. Then we will discuss it. Meanwhile, okay, you proceed. Let us see what it gives.
Okay.
I'll try to share it. Meanwhile, okay, Sandeep, sorry, Rahul, you proceed further. Let us see what you get.
Okay.
Uh,
So the other strain components, for now we have stick to the only x-axis, y-axis, and z-axis, and deformation along, extensions along only these axes. So if you have a crystal in 3D, you can there will be a like this face, uh, like this face. This is x-axis and y-axis. So the deformation along this face is given by exy, a plane, EYZ and EZX, and these are defined uh, in the angle between the axes. So to understand this, how this can be understood, like this will be the change like this. Okay, if I there this kind of deformation can take place on the plane with some angle. So okay, and let's bring in the equations. So what you do, the x dash y dash, you simply multiply these vectors with following the dot product rule. I dot I is equal to 1 and the other terms will be 0, and the multiplication of two terms like when you get epsilon yx multiplied by exy, these will be taken as a higher terms as of a square. So that's why I think you all can get these product x dash dot y dash. So you will finally end up with epsilon y of x plus and epsilon x of y. So one another way to understand these are from here. These are also called shearing strains. So what you do, there will be a change of angle like EYX. So These strains are known as shearing strains. Now consider the rotation of Ey x epsilon y of x of the edge AB, which is equal to dx. So suppose this AB A dash B dash is transformed with change with an angle A with epsilon y of x. So what you do, this is perpendicular upon base, which can be written as tangent of epsilon of yx. So B dash and the change in axis with respect to some angle, that is epsilon of y A dash B dash. So you simply write these values B dash curly v upon curly y and divided by this. So finally you can just take out the small change in the denominator, that is this will be very small, be neglected, so you end up with something like this. So similarly for the other axis you can do, this was for x epsilon of y of x. So other AC will be, you see here, there will be the two changes according to this plane. One will be tx of y, take this epsilon of xy and y of x. So that's why with respect to plane, a plane, uh, we will be taking two components along this. So the whole will be the sum of this e of y of x and epsilon of, and you will end up with this equations. And for the others you can also do. So any questions from here?
No, sir.
Okay, so you will end up with, if you multiply these you will get this. I mean, there is no z-axis, so you can just with respect to a plane that is along x-axis and y-axis, there is no z-axis, so you can just also forget about z-axis here. So x dash dot y dash, there will be only two terms containing, and this sum, and the next along y dash dot z dash, you will end up with this, and vice versa. So how to remember these shear strains? So one trick is to do that I have remembered, or जो मैंने याद करने के लिए, what you do, this will be same exy, yx, exy. Okay, so what you do, okay, so what you do, epsilon of y of x, okay, these are what direction, means e of x, this will tells you the change in along x. Okay, like I have written here. And the second subscript tell us displacement along which axis. So the second subscript here, x, this will be taken as if x x-axis and v is the displacement along y-axis. So you can just remember these terms like this. So like, oh, I have also done this, like, okay. So subscript of this term will tell you the change along x-axis, and the second subscript, that is y,
Rahul, your voice is not clearly coming. I don't know whether it's problem at my end or your end. What about others? Sandeep, can you hear Rahul properly?
Sir.
Is Rahul audible?
No, sir. No, sir.
There is some problem, maybe network from his end or what?
Yes, sir.
Rahul, can you hear us? Rahul, can you hear us? No, maybe he lost the network. Okay, let me quickly show you what I was trying to tell. I mean, how we can do this with using a Taylor
Hello.
series. Yeah, Rahul,
Yes, sir. Am I audible?
your voice was not properly audible for some
Oh,
time.
sir, do I have to from this slide? So can I explain this again?
Yeah, I think you need to explain this again.
Okay. Okay, hold on a second.
That's the trouble of network.
Yes, sir. Okay. So how to remember these equations? So what you do? Okay. 1 second. Okay. So how to remember these equations, that x dash dot y dash, if you multiply these, you can just
Your screen is
forget.
not visible.
Okay, screen is not visible.
Yes, Rahul, your screen is not visible. You have to share it again. Probably you got
Disconnected. Okay, sir. Yes,
disconnected, then your screen went off.
yes, sir.
Mhm.
Is it visible now?
It is coming. Wait, wait. Yeah, now you need to share the presentation part. Yours, yeah, this is okay now.
Okay,
You
okay,
go to
okay.
full screen.
Okay, thank you, sir. So to remember these equations, what you do, you can just forget about z-axis for now. Like this is a plane, and this axis is along x, and this is along y. So when you these two vectors multiply these two vectors, you will end up something like this: e of yx, and other terms, higher terms, can be neglected. So how to remember these equations? Like, what's the trick? So what you do, you can write the first subscript tells us about the change in what direction, that is epsilon of y of x, uh, of the first subscript, that is y here. It tells us about the change curly over curly y along what direction, along what axis. And when the second subscript comes in, y of x, second subscript comes in, it will tell you this x, it will tell you the displacement along x-axis is u, and y is v. So you can remember these like this. So I've taken an example here. So what you do, the first subscript tells us about the change along the direction, and the second subscript will tells you the displacement. So if there is y, it's y here, so this is v. So when you add these, and you can simply remember how these are transformed. So if you do for this y dash dot z dash, epsilon of xy plus this. So first subscript with respect to epsilon will tells you about, okay, it's z here, I think. Yes, yz, zy, and yz. So first subscript tells us about change along z-axis, and there is y. So y is the displacement along v, and second part, you can just the first subscripts will tell you about the change along y-axis, and z will be transformed displacement along w-axis. So that's how you can remember these equations, the also called shear strains, which will be which will be applied on the faces of the cube, the crystal. So that will be all, I think.
Is it done?
Yes, sir. So any question?
Yes, any question? PG fellows? I don't know if they are getting it or they are sleeping. PG fellows?
I don't know.
I also need to dress. What about my young students? Did you get the lesson or get the things or any questions?
No, sir, we get it.
Sure. What about others? Harish is saying he got it.
Yes, sir. I also got it.
You can just write yes, why in the comments if you don't want to talk.
Yeah.
Okay.
Okay. I mean, I'm just trying to fix up my things here, where I tried
Yes,
to
sir.
do this using Taylor series expansion. Maybe that will be helpful to some extent. Okay. Rahul, sorry, Sandeep,
Yes, sir.
have you done
Sir.
that for propagation of
Yes, sir.
waves along one direction?
Yes, sir. Yes, sir.
You are ready?
Yes, sir.
Okay, sir.
Okay.
So,
Let me quickly show
so,
up that Taylor series part, then maybe you can proceed.
sir. So, can I just stop presenting now?
Yeah. You can stop.
Oh, oh,
Meanwhile,
okay.
our
Okay. Thank you,
PG
sir.
students, if they have any questions, they can ask.
Yes, sir.
Meanwhile, I am beginning the things. I will need just 1 minute now. Just fixing up the things a little. Okay. Uh, Fade in very fast. Oh, sorry. Oh, just a minute. Okay, so let me share my screen now. This slide only, if it works. Right, so yeah, so now let us try to do this with this Taylor series. I mean, same thing done by employing that Taylor series thing. I hope that was the first thing which we needed to do. This was the displacement of any arbitrary point inside the body, and that is how it was written. I hope you remember that, in terms of U, V, and W. I hope I am audible there. Is it so?
Yes, sir.
Yes, sir.
Okay, fine. So now, if this is a function of this kind, having x component, y component, z component like this, then how does, and now we are retaining Taylor series only up to first order. Okay, so this can be written as x into del u over del x cap. Why so? Because this is the displacement with respect to origin 0, 0, 0, right? So one point is 0, 0, 0. So I hope you have studied derivatives, how we write a function. Now I haven't written the Taylor series exactly here, but I'm sure you can write it down in your notebook if required. For a one-dimensional function, f of x is equal to f at some point, say x naught plus delta x into del f over del x. That is up to first order, right? First order derivative only we are incorporating. I don't know how we can write. Sandeep, how you were writing things on your screen? Were you using some pen or you were trying to use it with the help of mouse? Sandeep, nahi, Rahul. Sorry.
Yes, sir. Sir, mouse.
Mouse
Yes, sir, I
से
was
लिखने
using
होता है?
Yes, sir. Yes, sir. In the presentation mode, sir, right में जाके right click से.
Presentation mode में right click.
Yes, sir. Pointers पे जा. Yes, sir.
Pointer options, and then I can use point
Yes, sir.
pen.
Yes, sir.
Let's try how it works. I don't know. Now, suppose we take a simple function, say f, and we want to write down f at x. I'm sorry, I'm very slow. Rahul was very fast. Then this is equal to what? F at x naught, right? Suppose we are expanding it around some point x naught plus delta x, or rather what we say x minus x naught. Okay, undo कैसे करते हैं इसको? Rahul, how to do undo?
सर अंडू नहीं कर सकते हैं सर. एस्केप दबाओ, एस्केप दबा के डिस्कार्ड चेंजेस कर लो.
डिस्कार्ड. अच्छा ये ओए यार ये पूरा ही चला गया.
सर ये पूरा ही चला जाएगा.
It's a very lengthy thing. Anyway, टेलर सीरीज सबको पता है, डेल्टा x into del f over del x. ठीक है? So if f x naught is 0, तो हम कैसे लिख सकते हैं f at x के ऊपर? That will be 0 plus something. तो क्योंकि हमारा r at small r equal to 0 है 0, reference point है वो. When small r is 0, that is why we are writing r of r is only this derivative part. और इसमें भी अच्छा वो स्क्रीन ही चला गया है. एक मिनट रुको. Okay, just a moment. मैं फटाफट से दिखा देता हूँ इसको. I'm sure you all can do this quickly. I will proceed because time is also getting up. Slide show. Yeah. So इसमें भी क्या था देखो. So this is your इसका derivative हमें लेना है. Now this is a three-dimensional function. So we have to take the derivative with respect to x, then with respect to y, with respect to z. U, r is a function of x, y, z, all three. So net change along x direction will be x into del u over del x, y into del u over del y, x cap. क्योंकि ये सभी x cap के component आएंगे. u के आप derivative लोगे जब x, y, z के respect में. That's what is going to come from first term. This is what is going to come from second term. then this is what is going to come from third term. And here we have only restricted ourselves up to first order derivatives. Is this clear up to here? Taylor series?
Yes. Yes, sir.
है ना? Okay, fine. Then इसको अगर आप सिंप्लीफाई करते हैं, I mean कुछ भी नहीं, ये x कैप पहले ही कॉमन भी ले सकते थे, that's the same thing. Then how will this come? So r of r, this is capital R of r, ये किसके बराबर था? I hope वो previous equation आपने देखा होगा, जो previous slide में था.
Yes,
That
sir.
was x into exx, x into eyx, ezx, and so on. ठीक है? Now if you compare these terms one to one, what you will get that यहां से अगर हम देखते हैं x component के साथ ये देते हैं, x के साथ क्या है यहाँ पे? Del u over del x. So x into exx will be x into del u over del x. That's your first thing. Second thing, third thing सारी यहीं से follow करेंगे, x into exy. So I don't know if effects आगे पीछे डल गए हैं, but anyway, x into exx, यहाँ से x into eyx किसके बराबर आएगा? y into eyx will be y into del u over del y. Y into eyx will be y into del u over del y. This one, right? Similarly, you can compare all those components. Y into eyy. So y into eyy will follow from this one. This is where it is sitting. So ये आपको compare करना है इससे. So you can see from here y into eyy will be y into del v over del y. That's what it is. So this way, by one-to-one comparison, आप इन सभी components को निकाल सकते हो. ठीक है? Is this clear?
Sir, actually problem is in derivative of ur.
हाँ, बोलो क्या problem है?
सर यहाँ पे अगर del u और del x अगर हम इसको विद रिस्पेक्ट टू x डेरिवेट करेंगे तो ये r का फंक्शन है, तो del u और del r करना पड़ेगा ना पहले हमें इसको, फिर उसके बाद r को x के रिस्पेक्ट में लेके जाना पड़ेगा.
R को
x के रिस्पेक्ट में.
पर यहाँ पे हम कंपोनेंट्स लिख रहे हैं ना ऑलरेडी. सो u जो है, आई मीन del u ओवर पार्शियल डेरिवेटिव अगर ले रहे हो तो del u ओवर del x लिख नहीं सकते क्या? व्हाट्स द ट्रबल? अगर
Yes,
आप
sir.
टेलर सीरीज फॉर ए 3-डायमेंशनल फंक्शन देखते हो, वो कैसे आती है? देखी है?
सर देखी थी वो, ऐसे ही थी वो भी.
कैसे?
मतलब वहीं पे प्रॉब्लम यही आ रही है सर कि मेरी del u और del x अगर हम इसको करेंगे फिर del r और डिवाइडेड बाय del x करेंगे तो वहां से x तो हमारा खत्म ही हो जाएगा, फिर x तो आएगा ही नहीं इसमें रिप्लाई में.
del r ओवर del x भी करते हो तो क्या प्रॉब्लम है आपको?
फिर x
What is
नहीं आएगा ना
r? r
सर.
is equal to x I cap plus y j cap plus z k cap. ठीक है? अगर
Yes,
मैं
sir.
del r over del x करता हूं तो क्या आएगा आपके पास? That will be just 1 into I cap. Simple.
Yes, sir. Yes, sir.
तो एक ही बात है ना, वो आगे आपके पास x cap.
हाँ जी सर.
del u over del x into del r over del x करते हो तो that is x I cap y j cap, वो x कंपोनेंट ही रिटेन करेगा. del x over del x will be 1. That's it. x cap आ गया साथ में.
Okay, sir.
Isn't it?
Yes, sir.
आ रहा है कि नहीं?
Yes, sir. Yes, sir.
Because r क्या है? r is x I cap plus y j cap plus z k cap.
Yes, sir. Yes, sir.
जब del r over del x करते हो तो I cap ही बचेगा. del r over del y करते हो तो j cap बचेगा. del r over del z करते हो तो k cap बचेगा. यहाँ पे I cap, j cap, k cap जो है वो x cap, y cap, z cap है हमारे पास.
Yes, sir. Yes, sir.
Right. So
Oh,
वहां
okay,
से
sir.
आपको ये सीधा सीधा मिल जाएगा.
हाँ जी सर.
Right. Similarly, exy को लिखने के लिए उसने कहा कि ये लिख लेते हैं. उसके लिए उसने कहा दिस शुड बी एक्चुअली इक्वल टू x डैश डॉट y डैश. x डैश और y डैश अभी अभी राहुल ने दिखाए थे. अगर उनका प्रोडक्ट लेते हो दैट कम्स आउट टू बी इक्वल टू दिस. ठीक है? ये प्रोडक्ट लेते हो तो इसको अगर आप मल्टीप्लाई करते हो, इसको मैंने यहां लिख दिया है अभी. ठीक है? सेम चीज कंटिन्यूस हियर. सो दिस विल बी eyx प्लस eyx इंटू exx, isn't it? नेक्स्ट टर्म होगी exy प्लस exy इंटू eyy plus exz into ezx. तो हम higher order terms को, because these elongations are small, so when elongations are small तो उनका product with same order of magnitude will be close to 0. तो इसको हम 0 पुट कर देते हैं तो ये हमारे पास किसके बराबर बचेगा? That's why this sign of approximately equal to इसके बराबर बचेगा, which was nothing but del u over del y del v over. इसी तरह से आप सारे components को निकाल सकते हो. दूसरी चीज आप ये बोलोगे अच्छा ये इसके बराबर क्यों लिखा? So actually यहाँ पे भी off the order है ये. It's not exactly. It is like, okay, this actually has to be equal to EXY plus EYX divided by 2. But okay, by factor of 2 को भी अगर हम हटा देते हैं तो off the order of वो उसने लिया है previous slides में अगर आप देखोगे. So that is how you can get all these strain relations. Is it clear or is it okay? I mean, that's how this can be followed simply by using Taylor series even.
Yes, sir.
And
Yes.
what Rahul said is also okay, no problem. But इस तरह
Yes,
से
sir.
भी सिंपल आप सारे निकाल सकते हो, क्योंकि
Yes.
राहुल जो कर रहे हो उसमें थोड़ा हेक्टिक है वो, कि हर चीज के लिए आपको पहले विजुअलाइज करना पड़ेगा, डायग्राम कोऑर्डिनेट सिस्टम बनाना पड़ेगा, isn't it, for every relation. So that is very lengthy.
Yes, sir.
है ना? तो विजुअलाइजेशन के लिए एक केस के लिए ठीक है, बाकी सभी के लिए करना है तो वो लेंथी हो जाएगा निकालने हैं तो. दिस इज सिंपल स्ट्रेट फॉरवर्ड थिंग. आई मीन टेलर सीरीज लिखिए, फर्स्ट ऑर्डर तक रखें, आगे चलें एंड देन सिंप्लीफाई करेंगे, कंपैरिजंस करोगे तो यू कैन गेट ऑल दोज रिलेशंस. ठीक है?
Yes, sir.
संदीप, आज का समय तो खत्म हो गया. कल आप करके आना ठीक से ना इसको, और कोशिश करना कि 30 मिनट्स में आपका हो जाए. टू द पॉइंट रहना है, ठीक है? संदीप, ऑडिबल?
Yes, sir. Yes, sir. Yes, sir.
या फाइन. सो फटाफट से अपना अटेंडेंस साइन कर दो सारे. और पीजी स्टूडेंट्स, ये टेलर सीरीज वाला समझ आया आप लोगों को?
Yes, sir.
ओके फाइन.
Yes, sir.
ठीक है. सो आई मीन वंस यू कंप्लीट योर अटेंडेंस, दैट्स ऑल फॉर टुडे. कल संदीप आप करके आना, पर कोशिश करना 30 मिनट्स में हो जाए वो, ताकि हम आगे प्रोसीड करें.
Yes, sir.
ओके फाइन. दैट्स ऑल फॉर टुडे.